All right, we'll get started here. Good morning, everybody, and welcome to the last Disney-McLane University class of 2016, and the first class from Disney-McLane's new headquarters. We have an exciting class for you today about a hot topic in the industry, digital mixing valves. And presenting is Jason Plageman with Disney-McLane & Associates. As always, if you have any questions, please feel free to use the chat feature at the bottom of the WebEx program. And as always, also, at the end of the program, we'll send you a ASPCU credit for attending the class. So without any further delay, I'll pass this on to Jason.
Thanks, Jim. I'd like to thank everybody for joining us today to go over the exciting topic of digital mixing valves. As you're all aware, we have an aging population in the United States where the 65-plus age bracket is growing at a rapid pace, and it's making control of digital or thermostatic tempered water in buildings much more important because of they're susceptible to airborne bacteria such as Legionella, and also their loss of sensory in their hands and arms and as they age. So we need these digital mixing valves to help them prevent scalding in situations like that. So for our overview today, we're going to really dig into the differences between digital mixing valves and thermostatic mixing valves. Now, when we're talking about a digital mixing valve, we're talking about a digitally controlled valve. Controlled by some of the items you see in the market out there that are truly a thermostatically controlled valve that they've just added sensors to. As we go on and look at these differences, you will see the benefits of having digital control and not just digital monitoring. We'll really dig into the added features and benefits of digital mixing systems, such as monitoring, something that comes with the system that you typically don't get on a thermostatic valve. And then look how they promote efficiency and safety in the hot water recirculation loop. So jumping into it on our first slide here, just the title page, we're looking at some pre-piped systems. A common problem with thermostatic mixing valves are piping issues. The digital offerings out there by several manufacturers do offer pre-piped systems, so this eliminates a lot of the on-site problems that we'll talk about a little more later in the presentation. So, thanks, Jim. So looking at the evolution of actuators for thermostatic or digital mixing valves, we've been mixing hot and cold water to provide tempered water actually since 1891, which was a bellows chamber, kind of a drum-shaped expansion and contraction device that would move a shuttle. In 1911, the market was introduced to the bimetal actuator, a paraffin or a bimetal actuator, copper and tin coil that expands and contracts to move a shuttle in a system to actuate between the hot and cold. 1919, we saw the liquid filled, again, expands and contracts due to water temperature. And then 2000, we saw the paraffin actuation come out, which we have a wax and copper dust filled cup that actuates a piston on the end that diverts between hot and cold water, very similar to what you see in your automobile thermostat. All these are very reliable, but they're susceptible to some common problems we see in plumbing systems. Around 2006, we started seeing the digital control offering. Key thing about this is these are electric motors, and the motors, unlike the actuators, the paraffin and bimetal actuators are located outside of the stream of water. If you look at the left side of the slide here, we see a bimetal coil and then a paraffin actuator below. And these actuators are only monitoring the outlet temperature and reacting to what that outlet temperature is. They're also in the stream of water, so maintenance issues arise quite often with hard water systems as these scale up and lose their thermal expansion and contraction properties, and also limit the movement of the shuttles between hot and cold. With the digital systems, where we have our actuator located outside of the water stream, we lose that continual maintenance issue of scale up of the actual driving motor or driving force behind the system. They're not susceptible to that change in scale buildup in the thermal property because of scale buildup, and they're very powerful to overcome any scale buildup on the internal system that it's actually actuating. Another key point are how we monitor the system and where the digital actuator gets its information. As I stated before, those paraffin and bimetal actuators are located in the outlet stream of the water. So they're really more reactive than they are proactive in maintaining a desired outlet temperature. Temperature sensors you see on digital systems, typically all brands are monitoring the inlet of hot and cold temperature and pressures, the mixed outlet temperature and pressure, and then usually they're also monitoring the return. These sensors are very high speed, they operate upwards of 10 hertz or 10 times per second, and they report this information to the digital control system up to every 6 seconds. So the reaction time on these valves is very quick compared to that of a thermostatic valve. With all these sensors, we also get complete monitoring of the system built right in. We know what we're sending out, we know what's incoming, and we see what's happening as it goes out and back in the system through the return. So we're talking about ASSE 1017 valves here for master mixing, and we got to take a look at the performance standard ASSE 1017. This standard states that valves will be tested 50% of their rated flow at a 10 psi drop, with an increase of water temperature of 25 degrees within 5 minutes. So they increase the water temperature 5 degrees a minute over a 5-minute period. As they put the valves through this, you can see the table below, they allow a permissible temperature variation from the set point. That variation on a large 40-plus gallon a minute master mixing valve is plus or minus 7 degrees. So that's a pretty big temperature swing, and we'll see that a little more in the next slide. But the standard allows that. That's what we're allowed to design and perform to. Another thing, important note we see on the performance standard is that cold water failure. It requires a reduction in flow of hot water under cold water failure. But that reduction in flow is not rated or limited by the standard. So they tell us we have to limit hot water flow, but we don't have to shut it off, which is a very key point that we'll see brought up a little bit later here. Sorry. Precision of digital valves, we were talking about the plus or minus 7 degree swing. Digital valves perform to this standard and hold tight plus or minus 2 degrees. Has a lot to do with the quick response and the anticipation of what's going to happen to that mixed water system as we're monitoring the hot and cold and return inlets feeding that valve or the mixing system. We see these temperature swings in a system typically when we're running a aquastat-based recirc system, as you see in the lower left-hand corner side of the screen there. And say we're drawing in cold water for a high demand, and our aquastat is up to temp. And as we start drawing hot water in the system, we start dropping the temperature of that aquastat, but we're bringing in cold water to make our tempered water currently. So we're bringing in 40, 50 degree water and mixing it with our 140 to get say 125 or 120 out of the mixed side. Once that pump kicks on, we're suddenly forcing into the cold side of that valve 80, 90, 110 degree water mixing with the cold before it gets to the mixing valve. So the mixing valve is actually seeing maybe 90 degree water. This is where you start to see a temperature swing, and you might see that plus or minus 7 degrees. With a digital system, the controllers operate the pumps as well, not an additional aquastat. So the same device that's controlling your mixing is monitoring and controlling the pump. So if they see that temperature drop on that aquastat and get ready to kick the pump on, it'll actually anticipate the valve being modulated, or the pump kicking on, and will modulate the valve to be proactive to the change in that cold water inlet the mixing valve is seeing. When this happens in a system with digital systems, we see maybe actually a little split-second blip of a degree or a half a degree in these temperature swings when pumps kick on. Thermostatic valve limitations. Common problems we see out there with thermostatic valves, as we talked about them being in the right in the mix of flow and reactive to situations, and also the limited flow under cold water failure. Because we stay open under cold water failure and don't have a positive shutoff on a thermostatic valve, and periods of zero flow or low demand, say overnight in a hospital or a nursing home facility, we're forcing through the mixing valve, because water is not compressible and we now have a closed loop, 140 degree water out of our water heater or boiler into the system. And because it's not compressible, we're not introducing any cold water. So this lack of positive shutoff on thermostatic valves is allowing for this temperature creep to happen. Once we see a demand in the morning, the first burst of water coming out of the system could be superheated up to towards 150 degrees and scald someone. Once they start getting flows, it drops back down as that valve is in there actuating. With the digital valves, we have a positive shutoff. So when we see, or the valve sees, that we're getting 140 degree and it's pushing through, it just simply shuts the hot side off, so you can't get that creep out of the water heater and into the system. You're simply just recirculating through a loop in the building until the temperature comes down to a point where the sensors decide we need to put some hot water back in the system, and then it pulls the water from the water heater. We'll see this mentioned again later when we're talking about energy savings. Thermostatic valves are also susceptible to cycling. Cycling typically happens when we're not piped properly, or we have a limited minimum flow. You see a lot of manufacturers on thermostatic valves, including ours, state in their submittals and their instruction manuals that these high-low mixing stations will maintain a temperature at a half gallon per minute of flow. But the big side note on that is based upon there being a properly sized recirc pump. If that pump's not properly sized, these valves will search high and low trying to hit and cover those flows. The non-high-low valves, the larger valves that do 40-plus gallons per minute, their minimum flows are around 5 gallons a minute. Sometimes in the building we only have a couple labs on with today's low-flow aerators, and we're only mixing 2 gallons of water, possibly of hot water. So we see these temperature fluctuations in the systems. With a digital valve, we have full control down to a half gallon a minute, and that's based on it monitoring the hot and cold inlets and returns and hitting the precise outlet temperature. So that was our overview of a comparison of the actual systems, of the mechanical components. Now we're going to get into some of the added benefits of the digital systems. security, ease of setup, building automation system connectivity, energy savings, real-time monitoring, and sanitation protocols. Security. This is a huge issue that I see a lot as we get called out to job sites to deal with mixing valves that are either searching or creeping or having issues with thermostatic valves. You have a maintenance guy that does it all. And with the mechanical valves or the thermostatic valves, we have locking mechanisms, simply a lock nut that tightens down on an adjustment screw. This guy knows how to operate a wrench, and he can come in and unlock that and make any adjustment he wants to the system, to the set point of the system. I've seen this recently in a large sports arena here in Ohio. I went out to look at a job, and there was a large high-low system feeding this building, and on the face of the valve where the adjustment handle was, where the lock nut was, the head of maintenance there had written different events that might happen in that said facility. And he felt it necessary to adjust that valve based on what the total attendance was at an event. So if they had a hockey game, it was at all the way to the right, let's say. And then if it was a concert where we might shut off half the arena, they would throttle it back a little more to the left because they wouldn't expect the volume to be there. So we want to get that maintenance guy out of the equation when trying to get these valves to operate properly. With digital valves, you are protected by digital passcodes, which can be in the possession of your building maintenance engineer and passed out to only those that they see fit to get in and make adjustments to a system. That being said, as we get into a little bit of the monitoring later on, anyone can go up to these systems or tie into these systems and get readings out of them on those flow rates or temperatures or pressures of the hot and cold mixed and return off the sensors, which is really beneficial in troubleshooting a job. On a mechanical or thermostatic system, we're simply looking at a gauge and going, something's wrong, but we don't know what, and we have the maintenance guys show up and start turning screws. So, digital setup and balancing. The simplicity of setting up a digital mixing valve is a huge benefit. Contractors install them. We know what we want as a set point. We've got the right person there to go through the passcode and get in the system and set it to what we need. So some of the systems out there are touchscreen and very intuitive. Others are, you have to bring in a laptop and plug in, and but also very capable of setting the system by picking a desired outlet set point, just typed right in. With the thermostatic systems, we're turning a screw and waiting for those gauges to adjust. On this screen here, you see the system box on the left-hand side there, and you notice that highlighted is manual mixing mode off. That's a standard setting as what a system should be like. As I spoke earlier about balancing, I'm losing Jimmy. System balancing. If we're not holding tight at plus or minus 2 degrees, our system has been set out to actuate the ball valve or shuttle by the digital actuator at 50% mix, hot and cold, or balanced at a specific voltage. Those actuators operate from 5 volts to 9.5 volts. So coming out of the factories, a true 50-50 balance of a system is set up at 5 volts typically. If we're seeing those temperature swings and they're not holding plus or minus 2 degrees, we simply go into these systems, put it in manual mix mode, and draw a demand off the system. A lot of taps are usually put right on our panels where we can draw a considerable amount of flow through a garden hose to a drain and allow the system to run itself in manual mixing mode. As it's in that mode, it finds the true mix point or percentage at 5 volts and gives that information back to the user to plug into the next line up, mix percentage at 5 volts. Maybe it's not 50% at 5 volts. Maybe it's actually 63% to balance the system because we have elevated hot or cold pressure. This is key, gets rid of the circuit sitters in a system. Very easy to do. It does it itself. You're plugging the information back in, and it eliminates that maintenance man from coming in and messing with not only the mixing valve, but the circuit setters that are around the mixing valve. Thermostatic systems, we walk into a lot and look at something like this. And we have contractors that install them, and a lot of them are very good and set them up and do a great job. I get called out to job sites sometimes to help them balance them because they have issues. And a system like this is a quad valve system that we're looking at. We have to adjust each of those valves individually, and then we have to create flow rates high enough to bring all the valves on at one point, simultaneously running at our high points. This can take up to 4 to 6 hours on a job site to get these dialed in properly. So imagine as we go through and shut off and isolate each one and set each one, waiting for the actuators to respond and the temperature gauge to settle out, over tightening or adjusting the screw is a common issue, and you're waiting. And then you shut off and do the next one. So you go through all 4, and then you got to bring one back up and add a second and add a third, and there may be some additional adjustment need to be made each time you do that as you elevate flow rates. Very time consuming and very tedious. The digital systems, last one I started up was about 2 weeks ago, and I was actually at the job site about 30 minutes. Contractor was there, engineer was there, did startup and training. The actual startup of the system took about 7 minutes. As we did the overview and training of our systems, we watched the system and saw what it was doing to make sure we had the set point and it was holding accurately for the next 20-some minutes. So the setup is a key benefit of digital systems. A next large benefit of a digital system is building automation connectivity. Healthcare facilities and hospitality are investing heavily in high-efficient equipment. They want to monitor this equipment and make sure it's doing and running at peak efficiencies as prescribed in their when they purchased the equipment. They did a survey on hospital construction, and 30% of them said their facilities would be upgrading building controls and automation systems within the next 12 months. The digital systems come with BACnet, Modbus, just about every manufacturer of system out there or format connectivity. So our system comes with all the set points on it and gives the readings, and this eliminates additional sensor points that the automation control contractor has to put into a system. So there might be a little money savings there as the system is getting set up. With the Volume Automation, we have constant real-time system monitoring. So head maintenance man, head engineer, whoever it may be sitting at their desk can constantly monitor the mixed outlet temperature, the inlets, and constantly see what's going on in their job, in their systems. This allows them to create profiles based on their system and what it's doing at different times of the day. It's very key information in saving wasted energy. There are also some options as we get into energy savings, would be on the next slide, to do additional flow and actually BTU monitoring that you can put with a digital system. I was a little ahead of myself. That's the next slide. So energy savings, we talk about approach temperature a lot with the digital systems. With a mechanical valve, approach temperatures is the delta between the incoming hot water and the mixed outlet temperature. Mechanical valves or thermostatic valves, this can vary from 5 to 25 degrees. So if we're wanting 130 out into a system to make sure the whole loop is sanitized, and we're going to knock it down again at point of source or point of use mixing valves, we might have to fire that boiler or water heater upwards of 150 degrees. With a digital system, the approach temperature is 2 degrees above the set point. So if I want to get 130 out, I only have to set that boiler for 132 degrees. Now, of course, we want to store hot water at 140, but the energy savings there from storing at 140 instead of 150 could be substantial over the longevity of the system. As I mentioned before, the hot water positive shutoff. We're running the system or zero demand on the system, and we're getting that bleed through the water heater, then we're adding water that's cooled down to that water heater constantly. When we have a positive shutoff on that hot side of the system, we can't force the 140 degree water out of the water heater. So it's staying stored in its insulated tank and should reduce the amount of recovery that's being made to keep up with the bleed through the system as cold water is introduced. Also with digital systems, as we do monitor the pumps and the pressures on these systems, we don't allow pumps to be deadheaded on your recirc pump if you're allowing us to control it. Deadheading that pump happens when we have such a demand on the system that the continuous run recirc pump cannot overcome the pressure drop being created in the mixing valve by that high demand. So as you see on our flow charts, as that GPM demand goes up, so does our CV factor or pressure drop. If we have a pump that can only pump 10 foot ahead or say 27 PSI, and we got a huge demand and we got a valve that's causing a pressure drop of 30 PSI, once that pump starts, that continuous recirc pump is running for no reason. It's just deadheading right into the mixing valve because it can't push past that pressure drop. So the digital systems will shut that pump off in that situation. That is done in the setup. You can put in the maximum pressure that pump can push. That's based on whatever pump is specified. And that will allow energy savings on those pumps running when there's high pressure drops in the system that they cannot overcome. Energy monitoring is a great option. As we talked about, we do the temperature and pressure monitoring constantly, but we can also do things with digital systems like adding vortex flow meters to the outlets and returns of these systems. What this actually does is allow us to estimate the energy consumption used for the domestic hot water system. So we can calculate the actual BTU usage used based on flow rates, temperature, and the return temperature coming back, and the differential between the mixed outlet and the return. We can also see the load demand in our building of the hot water system and what time of day is our highest load. So it will record and monitor all this and save it in these systems that can be accessed anytime that someone wants to take a look or has a question about the energy being used. When I'm here talking to a lot of engineers, when I go out and do presentations, this is a huge thing for LEED, that we are now adding some LEED points, or it helps earn LEED points to have systems that monitor things like this, the actual energy savings that we claim we're providing. We can do all these things in the buildings and specifications and get them installed, but if we can show that we're also monitoring to show that they are working properly, we can add to our LEED points for a project. I don't know if you guys can hear in the background, but we are in our new facility, as Jim mentioned, and we have a little construction still going on in the room next door. So if you can hear that, I apologize.
A little renovation.
Sanitation protocol. A lot of healthcare facilities, the VA has a protocol out that there must be an on-site protocol in place to deal with addressing Legionella. And of course, we know there's two ways we can do that according to ASHRAE 188P, which suggests we run 160-degree water for 30 minutes minimum through the whole system to sanitize the system and out of every outlet. Or we can do high chlorination. Both are very costly, but with chlorination, you have to it's a longer time frame because you have to thoroughly flush the system when done with the high chlorination. So these valves have sanitized functions in them. So if there's a Legionella scare, according to OSHA, we should heat the water to at least 158 degrees and maintain that for 5 to 20 minutes out of every outlet. Once we hit sanitize mode on these and set the temperature, of course turning our boiler up, and if we were sanitizing at 160 degree, if we have a thermostatic valve, we need to sometimes set that boiler temperature upwards of 185 degrees. Now we're over the limited temperature that those mixing valves can see and can cause damage to them downstream of the water heater. So with the approach temperature of 2 degrees, we can set the boiler at 162, pick our temperature on sanitation mode, and set our time frame for that sanitation to run. And we hit go. Then the facility engineers, the maintenance guys, the staff can go out and physically walk the building, stop by each outlet, make sure that they are running 5 to 20 minutes out of each outlet to sanitize the entire system. And then the digital systems have the capability of, once the time elapses, reverting back to the preset set point. And that doesn't mean strictly that, like on a mechanical, if someone went back and turned the screw down back to getting 140 or 130 degrees out of the valve. These digital systems, again, are monitoring that return. So after the time elapses, it goes into cool down mode and cools down the entire loop to the preset set point. That's saving a lot of time and readjustment of the mixing valve after we've performed this, and it gives the protocol in place with our digital master mixing valve being installed. It's something there already. It's not an additional protocol that needs to be addressed or added to a system. So in summary, key benefits of the digital mixing: the near real-time response. The speed at which these valves operate is beneficial, as we saw, as I talked about, with the recirc pumps kicking on under aquastat situations, so you don't see those blips in the system. I've actually been on sites and watched these. It gets quite boring as you watch the digital screen and you're looking at your set point and your mixed outlet temperature. As these valves hold at plus or minus 2 degrees, they also learn over time. so that tolerance gets tighter and tighter. And you see a screen set at 120, and you see it jump to 121 and instantly jump back down to 120 or 119 and bounce back up to 120 in a matter of seconds instead of a matter of minutes. So huge control and really mitigating liability on the design engineer and the facility because of the accuracy and the response time. So the next one, precise temperature control at plus or minus 2 degrees, helping us mitigate that liability at the facility. No inlet pressure constraints. I skipped over that one, I apologize, but on the thermostatic valves, we're limited to hot and cold pressure inlet differentials of less than 20% typically. As we saw, as I spoke about the balancing feature on digital valves, we can overcome that no matter what that pressure differential is. We can withstand typically straight out of the factory a 25% pressure differential, but it's not limited to 25% as a thermostatic valve may be. We have that option to go in and change that balance point in that digital actuator. Of course, it eliminates the temperature creep because we don't have the bleed through of the hot side of the valve because we do have positive shutoffs on digital mixing valves, and less affected by the water chemistry or scale. Scale is the biggest issue with mixing valves. Talking about going out and setting up systems and them operating properly when we leave. I talk to a lot of facility guys and they say, yeah, they work great until 6 months down the road when the effects of the water chemistry have gotten in the valve and either held open check valves or limited the travel of an actuator. So our next point there is little or no maintenance. Because these actuators are out of the flow of water, we eliminate that need to go in there every 6 months or yearly to maintenance the systems and clean the scale out. We do suggest a yearly inspection of the system to make sure it's operating properly. Not a bad idea to get in there and see if there's a little scale as well. But again, that scale buildup is not going to be on the motor driving the system. Easily installed. As I said, they're usually pre-piped or available pre-piped. Systems, we're going to tie hot, cold, return, and mixed outlet to the system. I've seen jobs where high-low mixing valves are in a system, and that maintenance guy or facilities manager that we see decided that it needed re-piped. I've seen that happen in jobs, and I just go crazy. And really, it just needs constant attention and maintenance to keep that system clean instead of changing the layout of the systems. Minimum flow with continuous running pump down to a half gallon a minute, no matter if that pump is oversized for the system or undersized. It controls down to a half gallon a minute. The building automation connectivity. As I said, the trend in the market is everyone wants to monitor and know what's going on in these buildings so they can create profiles of what their systems are doing at given times of the day. And this is huge for those lead points and getting true flow data out of the system and BTUs consumption. So I appreciate you guys coming on today. I'm going to leave this time for any questions that have popped up in the text box here, the chat box.
Yeah, thanks, Jason. It was a great presentation. We will open it up now for some questions. We have had some come through. Let's start out with the first one. Would electric heat trace in lieu of a recirc pump resolve some of the problems with traditional high-low mix or thermostatic mixing valves?
We do see heat trace on recirc systems to maintain that loop, but it does not eliminate the problems we have with thermostatic mixing valves with the conditions of water and now we have another maintenance issue with making sure that our electric heat trace is up and running properly. That's just another system that a maintenance man or facilities manager may need to or desire to dig into as we add components to the system to modify.
Here's another question. Could UV light negate the need to hold hot water temperatures high? In other words, can UV treating remove bacteria, Legionella, with a system that runs at 120 has no master mixing valve at all? This one actually might be a question for OSHA. What we can tell you right now is that OSHA requires the 158-degree hot water sanitization period of 5 to 20 minutes, I think.
Yeah, out of each outlet.
So this might be a question you may want to ask your local OSHA representative, but what we can tell you right now is that OSHA requires that hot temperature of the water. One more here. What is the typical cost compared to the thermostatic mixing valve system?
Costs of these, as expected, are considerably more than a typical thermostatic system. But you got to look at the maintenance costs required on the thermostatic system, and that limiting the liability and the additional features such as sanitation protocols added to the system. I've seen for high, low, large volume systems, it could be 50 to 75% more for a digital system. When we sit down with building owners and talk to them and show them these, they like the simplicity of the systems and the added benefit of the precision at which they operate.
Well,
that helps.
Any more questions, just let us know. You can always give me a call or shoot me an email. So yeah, again, thanks again, Jason, for the great presentation. And thank you all for supporting Disney-McLane University in 2016. Stay tuned for our new syllabus coming out for 2017 classes. You should see that soon. Also, if you want to see a recording of this class, just check out our YouTube channel. Look up Disney-McLane and Associates on YouTube, and you should be able to find us. So yeah, if you got any more questions, please just feel free to give me a call or shoot me an email. And yeah, I want to thank you again, and I hope you have a Merry Christmas and a wonderful New Year. See you later.